Good morning, friends, my students and dear learners. This is the second lecture on a fast reactor. So today we are going to discuss the concept of breeding and the reactivity estimation mechanism. Normally, conventionally, in fast reactor, we are working in nuclear field. There is a famous methodology of 5 feedback mechanism. I'm not going to discuss all these things in details because it will take time. I'll try to give a glimpse. So always, this is right now it is 6:45 morning. So always I used to remember my gurus because I'm a Vedic astrologer. So the planet Jupiter is responsible for your knowledge, your humbleness, your education, all these things. So always better to increase. If your Jupiter is weak, the Jupiter planet in your birth chart, if your Jupiter is weak or it is conflicted or the degree of Jupiter planet is less, means not favorable or weak, then we need to increase. Even though it is your Jupiter is good also, so always better morning, early in the morning, after getting up, you remember your gurus and respect seniors. Automatically keep yellow colors nearby, donate yellow food to poor, so this will eventually increase your Jupiter, so which will in turn increase your knowledge and learning. By the way, I always used to remember my gurus. These all things I learned from my guru, Dr. Chelapandi. I always remember him. So anyway, today we will be discussing about concept of breeding and reactivity feedback mechanism, how to estimate the reactivity in a sodium cooled fast reactor. So prior to go in details, we should understand few terms. We know in the fundamental mechanism behind any reactor, so far whatever the 3-stage nuclear program I explained in my previous lecture, it is dependent on nuclear fission. So in nuclear fission, basically neutron is getting generated, which is doing the next bombardment with the fissile material. And to sustain this mechanism one by one, means to sustain the chain reaction, the number of neutron produced per fission as its energy is very much important. Okay. So in this aspect, one term is very important, which is called energy spectrum. We know the energy density function or probability density function, which we studied in engineering. So I am not detailing, I am assuming all you know that. So the neutron released during fission can be divided into 2 categories. One is prompt neutron, another is dead neutron. So prompt, you by name, as the names indicates, prompt neutron is the neutron which is emitting instantaneously by a nucleus when it is undergoing a fission. On the other hand, the delayed neutron are the neutron which is emitted by an excited nucleus among the fission product at an appreciable time interval, after some time. Okay. So as the fission fragments having higher energy, if you see the mass distribution, so eventually the prompt neutron will must have higher energy. On the other hand, the delayed neutron will have less energy. Okay. So let us see it graphically. So there are two graphs. This is the energy distribution of a prompt neutron, and this is the energy distribution of delayed neutron. Okay. So in this case, the x-axis is the neutron energy in mega electron volt, and this y-axis is the probability density function, energy distribution function. That is that is the probability that a particle is in energy state at energy E. Say this is E. This is E, and this is your Xe or eta or whatever may you tell. This is basically, it is Maxwell fission spectrum. That means at the number of fission, the number of prompt neutron, the probability of number of prompt neutron is this point is this much, which having energy E. Okay. So in the graph, it is very much clear that the probability, if you take the maximum or the average, so this area, okay, this area. So in case of prompt neutron, the energy is varying from say 0.2 mega electron volt to 1.4 mega electron volt, or average, if you do the averaging, it will be 1 to 2 mega electron volt. Okay. But if you see here, x-axis is relative yield, so you should know what is yield. Okay. Nuclear fission splits, we know the nuclear fission splits heavy nucleus into two lighter nucleus. So this yield refers to the fraction of fission product produced per fission. Okay. So neutron also is a fission product, so that is represented here in case of delayed neutron plot, energy neutron. So the y-axis is relative yield. Okay. So the number of neutron, the ratio, it is relative yield means number of neutrons by total fission fragment. So that is represented in x-axis. Here you see the peak is occurring here, which is maybe, so this one 0.5, so this is 0.2, 0.7 or 0.6 mega electron volt, and average it will be somewhere in this region if you take the average. So here you see the average energy of a prompt neutron is 1 to 2 mega electron volt, and the average energy of delayed neutron, it is 0.3 to 0.6 or 0.7 mega electron. So this graph represent that the delayed neutron, the prompt neutron is but the prompt neutron have higher energy. Okay, this is again a typical conversion process pictorially, which is converting the fertile material to fissile material. So you know, this case is our PFBR, and this is where the blanket is uranium 238, which is a fissile. There will be a neutron carrier, then it will become uranium 239, and finally with gamma and beta decay it will convert plutonium 239. This is again fissile. So this is happening recursively. Okay, so gamma and beta decay, we know beta decay means it is at mass number will not change, but the atomic number will change by 1, increase by 1. In gamma decay only energy will change, no change in mass and atomic number. In alpha decay atomic number will decrease by 2 and mass number by 4, all we know that. So these things is happening in our PFBR, and this is our final target: utilize the sodium reserve in the country, where the plutonium will be used and thorium blanket will be there, thorium 232, and after that, capturing the neutron, this thorium will convert temporarily, momentarily or intermediately to protactinium 233, and then it will convert finally after a beta decay with a half-life of 27 days, it will convert uranium 233, which is a fissile material. So this all I have discussed. Now here we will understand the concept of breeding. So breeding is a process of converting a fertile material to fissile materials, and it is quantified by a term called breeding ratio, which is the ratio amount of fissile material produced to that of fissile material destroyed, either through fission or through the capture. So let us take a typical example of our PFBR. So here, this is the, say, plutonium 239. Okay, plutonium 239. So plutonium, say plutonium 230 or uranium 238, you can take here, this is as uranium 238. So one neutron, it is absorbed and it is converting finally by plutonium 239. Okay, so after here one neutron is absorbed. Say if this fission is producing n number of neutrons, then one neutron is absorbed by this nucleus to convert it, then the remaining neutrons are n-1. But again, there are, say, the p number of neutron is going out of the core, getting leakage, or it is absorbed by something but no energy produced. So the finally neutron remaining after loss and absorption is definitely n minus p minus 1. So this is the balance neutron after a fission, after a successful fission. But to do the next fission, for the occurrence of next fission, at least one neutron should be available after this absorption and losses. So definitely this value will be greater than equal to 1. So my n is greater than is equal to p plus 2. Even though the macroscopic cross section is sufficient enough, or the structural design sufficient enough that there will be no loss, p even though 0, so definitely at least the n should be is equal to 2. So for breeding to sustain the chain reaction, the number of neutron, the minimum number of neutron produced per fission should be at least 2. Okay, so in case of typical sodium cooled reactor, fast reactor, around 45 neutrons are absorbed by the sterile capture, which is nothing but the neutron captured by the nucleus of the moderator or the structural material, fuel cladding, control rods. Okay, these are the called sterile capture. So 45 neutrons are absorbed by the sterile capture, and 25 of which are absorbed by fissile nucleus itself. It's a which is called parasitic capture. The around 60 neutrons is getting leaked out. It's going outside of the core. Okay. So around 50 neutrons are absorbed by the capture in fertile material. So here, as I told, it is uranium 238, which is in the blanket, and it is converting that uranium 238 fertile to fissile plutonium 239. And other 10 neutrons approximately it will be captured by the structure of the reactor, like absorber and safety rod drive mechanism, the vessels, coolant, all these things. Here one thing also we should understand, which will be useful for to understand the concept of our successive lectures, is the conversion ratio. Is the number of fissile nucleus generated from the fertile nucleus divided by the number of neutron absorbed. So inside the core, this is, I am giving a typical figure. You can refer any book, it will be available. So in fast reactor core, the conversion ratio is approximately 1. So it is self-sustaining. The chain reaction is self-sustaining in core without any external feed. But if you add the blanket, of uranium 238, then your conversion ratio is 1.3. So that is, the breeding is gained by 0.3 with the blanket. So definitely blanket is helpful to increase the conversion ratio. Now the question is whether is our people used to tell whether that this kind of chain reaction and the multiplication, means the neutron production in a fast reactor, it is happening within a fraction of seconds. So whether to operate the reactor is safe or not. But the structural design of reactor is much more safe, that we are going to discuss. The construction of its virtue, the reactor is very safe in contrast to bomb. I'll give you the link, basic concept of fission. There I explained how the bomb is the working principle of bomb. So there the structural construction is entirely different. that the leakage, absorption, all these things, it will be not there. So it is because we know for bomb need the supercritical reactor, but for power generation we need perfectly critical with multiplication factor 1. Okay, that means the proportionate constant of the neutron reproduction should be alpha, which is that we are going to discuss. That should be 0 in case of reactor. So normally the change of neutron with respect to time, these equations and all these things, it is explained in my video called Basic Concept of Fission, which that link I will be giving in the description of this video. You can browse it. So this is established from Fick's law and diffusion equation. So that is very clearly, elaborately explained there. I am not telling here to save time. So the rate of change of a neutron with respect to time is proportional to number of neutrons generated by its lifetime. So to remove the proportionality, we need to have a constant. Here I am telling it as alpha. So here n is the number of free neutron in the reactor core, and tau is the average lifetime of the neutron before it escapes from core or before it is getting absorbed. So it's a very simple differential equation with the boundary condition, say the initial number of neutron is n0. So if you solve it, if you integrate it, it's a simple differential equation. So n by n0 is equal to 1 plus alpha at t is equal to 0, n is equal to n0. So I am considering that boundary condition. 1 plus alpha divided by to the power 1 by tau. It's an exponential function. Okay, so my n is equal to n0 into 1 plus alpha to the power 1 by tau. This is the equation. It's an exponential function. So you know it is very rapidly exponential, means it is increased like this. So if alpha, so the nature of reactivity depend on the value alpha. So proportionality, that proportionality constant. So alpha, if it is positive, so this is called, reactor is called supercritical. It's very quickly, very fast. This means the explosion may take place. If it is negative, it is subcritical, because the number of neutron, it will get reduced with respect to time, and after some time it will become 0 and reaction will stop. With alpha, exactly, if alpha is equal to 0, so this equation will turn to n is equal to n0 into 1 to the power 1 by tau. Whatever may be the tau, 1 to the power something is 1, then your n is equal to n0. That means the number of neutron produced after a fission is nothing but the neutron which we used to bombard the fissile material. So this is the requirement for a reactor to get critical. Even though in my that basics of basics of fission, in that lecture clearly it is given on the differential equation how to estimate the critical mass and the critical volume. For calculation simplicity, I have considered a spherical reactor, spherical geometry, and this geometric buckling is a very important feature there to decide the criticality of the reactor. Okay, so now take a typical value of alpha. Say alpha is equal to, normally say it is 0.01. Okay, and the lifetime of a neutron is around around 1 millisecond. So now if you put this value here in this equation, so what will come? Your n is equal to, say your initial neutron, it is 1. You assume initial neutron is 1, which is used to bombard a fissile nucleus, and in that reaction the alpha is 0.01 and the average lifetime of that neutron is, first neutron is 1 millisecond. So what is the equation? Now if I put the value, so it is 1 plus 0.01 to the power 1 by 1 millisecond, that means 1000. What is this value? 1.01 to the power 1000. It is around 10,000, correct? Now you see in ideal case, if you are giving one neutron, your structure is designed such a way that the absorption or the leakage is optimal or ideal, then it will suddenly, within a second, it will generate 10,000 neutrons. So the reactivity will increase in that ratio, which is really uncontrollable. We cannot control. But by the construction of the reactor and its virtue, it's not happening so. You understand the concept of delayed neutron, which having less energy. So this will oppose this thing. So even though the individual prom neutron having a lifetime of 1 millisecond, but due to the delayed neutron, it's the average lifetime of the prom neutron is reduced to 0.1 second only. 0.1 second. So now if you write down the equation, so it is 1.01 to the power 10, which is around 1.1. So now you see here the multiplication, the neutron multiplication is increased by only 10%, which is more or less controllable. 10%. It's not means one neutron it will become 10. It is quite controllable. But in the previous case, in the ideal case, it was ideally it should be 10,000. 10,000. So which is not at all controllable. So that's why I told the reactor control becomes safe by its virtue of its construction. So here typically 5 to 10% increase it will be there. So which can be maintained easily by our absorber rod mechanism. This is the last topic of today's lecture. So we know who are working in core temperature monitoring. So you know in the reactor, very interesting thing, because this if anyone want to know any one of the estimation, say the Doppler axial or that coolant reactivity, the radial expansion of the structure, and the CSRDM due to reactivity change in CSRDM and DSRDM, there are 5 paths. So that's why this things is called five feedback mechanism. So it is open to the people who are working in core temperature monitoring. So if anyone interested to know all the feedback path in details, I am ready to explain, but that will be separate discussion. I will not tell in the open forum because there are some secrecies there. So exactly from where the which thermocouple is going where and how it is, because it involves a lot of calculus and the stochastic process. It's a stochastic process, stochastic estimation and calculus. It's a very interesting. I will, if anyone wants to know, I am ready to explain. It's a very interesting derivation in mathematics. So here this, you see there are few colors. So here it is a green color, red color and the black color. So green color is representing the negative reactivity. So what is reactivity? Basically the K is called the, in reactor physics, K is called the multiplication factor, which is n0 by n0. So the change is K, this is n0, sorry, n by n0. Okay, so the reactivity is nothing but the change of this K. This will change the reactivity. Okay, so here what I was telling, the core temperature monitoring become very critical phenomena, and with that only we are going to estimate all these things. All these things we are, because these are all this Doppler and this the reactivity change. How reactivity will change? Okay, how reactivity will change? Because basically fuel will be inserted in a fuel pin rod. It's a structural material, and due to temperature, there will be a change. There is an expansion, radial or axial, whatever may be. There will be a change in the volume. If volume is getting changed, then your density of the fuel also will get changed. Anyway, I am not good in English. I am a North India, so I am much more fluent in Hindi. My English is bad, so you please all bear with that. My pronunciation also may not be good, but I will try to explain. Hope my language will not matter. So this is structural. If there is a structural change, then in turn the density of the fuel will also change. So if that change, then in turn the absorption, because the macro in Fick's law you will be seeing the concept of macroscopic cross section. So this macroscopic cross section will change, which will change the delta K. But here the thing is, the reactivity change is based on the structural change, but there is no direct mechanism. We can direct measure the strain of the structure inside the reactor. Only the parameter which is in our hand is temperature. So temperature monitoring is very important in a reactor for its reactivity control. So this diagram is showing that. I will explain it in brief. Okay, so if there is a perturbation, then it will be reflect in coolant flow, the inlet temperature change, or say there is a external perturbation, there is a change of reactivity, external reactivity we added or withdraw, which is called not withdraw, it is say added. So this is called reactivity insertion. So how these things is going to change? So here you see this delta, the change in delta T in fuel, delta T in clad, and from there, as I told, it involves some mathematical derivation and stochastic process to estimate the absorption, leakage and spectral. And this is we already understand what is called neutron spectrum. we have seen graphically the spectrum of prompt and fast delayed neutron. So that x-axis, if you remember, the x-axis, this is basically not delayed neutron, this is for prompt neutron. So in that curve, the x-axis, the y-axis is the probability. Y-axis is the probability. So from there we can find out the number of prompt neutron having a particular energy. So this change in the change of neutron, the change of neutron absorptions, leakage, the spectral neutron density, all these things will be estimated in this way. From the fuel delta T, here is the absorption, the delta T, the leakage, the coolant delta T, spectral as well as the leakage. From the grid plate and the load pad, it is also leakage, but this will be used to estimate the radial structural change, and from that we will estimate the change in reactivity due to radial structural change. And these are the CSRDM and DSRDM delta T, and this is the main vessel delta T, and from there we will be estimating the change in absorption, neutron absorption, change in neutron absorption. From there we will be estimating the reactivity change due to structural change of CSRDM and DSRDM. So hope this concept you have understand. So basically, as there are five feedback, so this is called 5 feedback mechanism, okay, and the parameter through which all these things is getting estimated is only the temperature. So core temperature monitoring become very important. Here 5 feedback path is there, finally all added together and estimating the reactivity. So that's why it's called 5 feedback mechanism. So finally we are calculating the Doppler reactivity change, axial reactivity change, coolant reactivity change, radial reactivity change, and the reactivity change due to CSRDM, DSRDM. So this green color is contributing the negative feedback. The red color is because, as I told, this is the prompt neutron. So this having some higher energy. Okay, so this is a positive feedback, and this black, it is the sign is dependent on the design. So this design, I am not supposed to tell what design is adopted and how it is positive or negative, so that I am not telling, I am sorry. So this is the 5 feedback mechanism, and we will understand slightly with the picture, a generalized picture. So you see, these are the typical core. So here you see, this is the axis. Okay, so this is the top load pad, and this is the above core load pad. This is the core barrel, and this is the fuel assembly bowing. So bend. So this red color, it is the radial expansion. Anyway, here we used one Doppler. What is called Doppler in nuclear reactor? So this is the broadening of reaction. This reaction cross section means that enlargement of the macroscopic cross section, sigma A. You can see my nuclear physics, that video I'll give in the description. There clearly explained what kind of, how it is established from the Fick's law. Okay, so this Doppler in nuclear physics is nothing but the broadening of reaction cross section increased by temperature. Okay, so you see, this is the grid plate. This is the grid plate. The grid plate also getting expanded axially, radially, and this arrow, vertical arrows, represent the axial expansion. Axial expansion in reactor core shielding, all these things. As I told, inside this fuel will be there. If there is a axial expansion, so based on the Poisson ratio of the structure, there will be radial decrease. If the radial decrease, then the fuel also. So in the radial, there is a decrease of, basically there is a decrease of radius. Okay, and there will be a increase of length, which will reduce the density of the fuel. So there are two things happening. Fuel density, it will reduce, and your radius also it will decrease. So both the case, it will confirm, it is indicating, or it is confirms this decrease of radius is confirming the increase of leakage. Radius means radius chota ho gaya, so very quickly the neutron will go out from the fuel. So that's all. No further reaction will take place. Density decrease means your critical volume should be less. That concept, it is there in my basics of fission video. You can see that. So all these things basically, so that's why the sign of the reactivity feedback is defined as per that. So hope today's discussion you understood. I tried my level best to explain you. If any question is there, you can write in the description box, or there my WhatsApp it will be given, so you can reply there. Anyway, now it is 7:20, so I have to be ready to go to office. So thank you so much. Thanks for your patience. Good day.